What is ECoG, and how do electrode grids work in BCIs? Imagine being able to control a computer or a robotic arm just by thinking about it. That's what some brain-computer interfaces are working toward. Today, we're exploring a key part of that technology called electrocorticography, or ECoG for short. ECoG is a way to record brain signals directly from the surface of the brain. It involves placing tiny metal contacts, called electrodes, on the outer layer of the brain, known as the cerebral cortex. These electrodes sit just beneath the outer membrane of the brain, called the dura mater. To do this, surgeons perform a procedure called a craniotomy, which is a small opening in the skull. Once the electrodes are in place, they pick up electrical signals generated by neurons firing in the brain. Because the electrodes are directly on the brain surface, they get a clearer and faster picture of brain activity than non-invasive methods like electroencephalography, which record signals from outside the skull. These signals are much more detailed and can be used to understand what the brain is doing in real time. The electrode grids used in ECoG are made of tiny metal contacts, often of biocompatible materials like platinum. These contacts are embedded in flexible materials such as polyimide, which helps the grid conform to the natural curves of the brain. This flexibility allows multiple electrodes to sit comfortably on the brain surface and record from different areas at once. Each electrode detects the combined electrical activity of neurons underneath it, giving a map of brain signals across a wide area. In brain-computer interfaces, these signals are processed through several steps. First, the signals are captured and amplified. Then, they are cleaned up and broken into smaller features. These features are analyzed to find patterns that match specific thoughts or intentions. For example, certain patterns might indicate someone wants to move a limb or spell out a word. The system then translates these patterns into commands that control external devices like prosthetic limbs or communication tools. Compared to other invasive methods that involve electrodes penetrating into the brain tissue, ECoG offers a good balance. It provides higher quality signals than non-invasive techniques but causes less damage than electrodes that go deep inside the brain. Advances in technology have led to micro-ECoG arrays with many more electrodes packed into a tiny space. These arrays improve the detail of the signals while minimizing any potential harm to the brain surface. ECoG-based brain-computer interfaces are already helping people with paralysis regain some control over their environment. Because the signals are more stable and less noisy than other methods, they allow for faster and more reliable control of assistive devices. Researchers are continually working on better materials and designs to make these systems safer and more effective for long-term use. In short, ECoG uses grids of tiny electrodes placed directly on the brain surface to record electrical activity with high clarity. These signals are then decoded by brain-computer interfaces to help people communicate or move prosthetic limbs simply by thinking. It's a promising step toward restoring independence for many individuals and opening new doors in neurotechnology.